All right, guys. We've been taking a look at different types of functions that are going to occur somewhat naturally in the discussion of the Laplace transforms. In the previous section, we took a look at the step function. We want to take a look at another extremely important function. And this one is by far much stranger than that of the step function. However, it's just equally as important. And the function that we want to take a look at is what we call the impulse function. Now, this function also goes by different names. It goes by impulse function in the context of electrical engineering. If you've ever taken a physics class, especially one in electromagnetics or electromagnetism, this does actually go by a different name. This is also called the Dirac delta or Dirac delta function. So two different names that denote the same thing. Now, just like the step function, it can take on one of two values, and it has one extra defining property. The symbol that we use to denote the impulse function is the Greek lowercase delta, and by definition, it can either take on the value 0, or very strangely enough, it can take on the value infinity. Now, it will take on the value of 0 whenever the argument inside of the delta function, whenever it is something other than 0, right? So over here, this is if x is not equal to 0. And it will literally blow up to infinity at one single point, and that's when the argument inside of the delta function, again, let me highlight that, when, oops, this in here happens to be 0, right? So here, this will be infinite if x is equal to 0, right? Now, there is another property, and this is by definition. And if it seems strange initially, uh, don't worry, it seems strange to everyone that sees it for the first time as well. It has the added property that if you actually integrate from infinity to minus infinity, the Dirac delta function, like this has the property of being 1. Right? Very strange property, but I can guarantee that it's going to be extremely, extremely, extremely useful. Right? Now, strictly speaking, this itself is not, even though we call it a function, it's really actually not a true function in the true sense. Remember that one of the requirements for something to actually be a function is that it must have a finite value everywhere. Right? The fact this actually blows up to infinity at one point in space makes it not a function. However, it is what they call a generalized function, or it's also known as a distribution. Now, there are various types of distributions that will actually lead to this type of behavior. I'm actually going to very briefly discuss one and only one. So, and this is a distribution that leads to the impulse function. And here I'm actually going to change the variable. I was talking about x, here I'm actually going to talk about t. Suppose that you actually had the following function itself. Suppose that you actually had a square like this, uh, whose length was some value epsilon. So here we actually have this rectangle, and whose height happens to be 1 over epsilon. Looks like I erased more than I had wanted. Let's do that again. So here we have our axis like this, and the height there is trying to make it neat, 1 over epsilon. Notice that by its property, right, the inside of here, the area, well, its length times its width, right? Its area happens to be 1. On top of that, take a look at what happens when you actually end up shrinking epsilon. So take a look at what happens when as epsilon starts approaching 0, right? So as epsilon starts approaching 0, well, its length, right, starts shrinking, but its height, because it's 1 over epsilon, it starts actually getting bigger and bigger and bigger and bigger. So you might end up with, as it shrinks, a series of functions whose area is still 1, as this keeps on getting smaller and smaller and smaller. Right? So the area here inside of each one of these successive rectangles is always 1, but as epsilon starts shrinking down to 0, notice that you end up getting the behavior that you actually wanted from the impulse function, namely that it is 0 everywhere, except at uh, the singularity, it blows up to infinity. And there are many other types of distributions that, again, lead to the exact same type of behavior. Now, some of the most important properties of the delta function, or the impulse function, and I can guarantee that you are absolutely going to adore the impulse function for these properties, because it actually makes the mathematics extremely, extremely easy. The first property is the following. Suppose you actually take some other function. I don't care what function it happens to be. Just say it's f of t. And you multiply this by the impulse function. Then one of the things that's going to end up happening is that this itself is going to be the same thing as f of 0 times the delta function. So notice that the trick here, in some senses, and this is the fundamental thing, is that these two products are absolutely identical. Now, the rest of the arguments completely hinge on the idea that this is true, right? So make sure that you understand why. And again, it happens to be because everywhere except 0, where the argument of the impulse function is 0, well, I'd be multiplying f of 0 by 0, because outside of that, it happens to be 0. So this identity is extremely important. Now, what happens if I end up integrating this? So suppose that I integrate this. Well, if I integrate from minus infinity to infinity of f of t times the delta t, well, as we mentioned just a second ago, this is the same as the integral from minus infinity to infinity of f of 0 times the delta dt. F of 0 is constant. This is constant. I can bring that completely outside of the integral. Right, so this is the same thing as f of 0, the integral from minus infinity to infinity of the impulse dt. But by definition, what is this integral? By definition, that is 1. Right, so over here, this is f of 0 times 1 by definition, or f of 0. Notice that what this has actually done is it has uh, essentially, whenever you take any function whatsoever and you multiply it by the impulse function and you integrate, and this is actually crucial, you integrate with those bounds over a place where it becomes infinity, what happens is that the function itself only takes on that value. There's no other work to do. It simplifies integrals tremendously, tremendously. Now, keep in mind that one of the kind of additional properties is that you don't actually have to integrate from infinity to minus infinity to have this actual behavior. One of the things that suffices is that you actually end up going over wherever the delta itself, wherever the argument of it actually happens to pass through that. And I'll show you here an example. Another thing that's important is sometimes that um, impulse function, it's not necessarily true that it has to 100% occur at 0 all of the time. Just like what we did with the step function, where we could actually have that discontinuity in the step function going from 0 to 1 at different times, we can do the same thing with the delta function. So we can actually have the shifted one. So if we consider f of t minus a, well, this by definition is 0 if the argument is not 0. So here, this is if t is not equal to a, but it does blow up to infinity if t is equal to a. Okay. Now, diagrammatically or graphically, that means that our delta function that happens to be shifted, suppose that this is a right here, right? Well, it's absolutely 0 everywhere, and then here it blows up to infinity at the place where the argument, again, happens to be 0. Now, in addition to this, we also have, again, the fact that if you integrate over the value that happens to make that delta function 0, that integral happens to be 1 as well. So if you actually, for example, here I'm going to restrict, I'm not going to integrate from minus infinity to infinity, but suppose that I actually integrated, let's say, from a minus a tiny little bit to a plus a tiny little bit, and I considered the impulse of t minus a dt, well, because over our integration bounds, we are integrating over the place where that is actually 0, then this itself is going to be 1 as well, right? Keep in mind that had these bounds been slightly different, so for example, suppose that we didn't actually integrate over the place where it makes it 0, then that integral with the delta function itself would have been 0, right? We can also do the integration with some sort of function multiplying it like this, right? Well, we do know that this portion right here, just as we had argued previously, well, uh, it's going to be 0 when t is equal to a. So this portion itself is the same thing as f of a times delta t minus a. If that's the case, then f of a is a constant. I can bring it outside of the integral, and then I would be integrating the impulse function over the place where we have that singularity. This by definition is 1, so this just takes on the value of a like this. The last thing that I actually want to say about the impulse function is that it is intimately related to the step function. So step function relation to the impulse function. So let's actually go back and take a look at this function. So here, suppose that we had the step function like this, u of, let's say, t minus a. Let's say a is here. Well, we know that the step function is going to take on a value of 1 for values greater than a, and it's going to take on a value of 0 for values less than a. And consider the derivative of the step function with respect to time, right? Well, the derivative of 0, it's still constant. It's going to be 0. The derivative of 1 with respect to time is 0. The only place where it's not 0 is exactly at the place where there's that discontinuity, and the derivative of discontinuity is infinite. So if you actually take the derivative of the step function, one of the things that you get is the impulse, right? And you should be very clear that that's the case, because again, outside of this, the derivative of 1 or 0, that's constant, well, they're all 0, except at the singularity, where it blows up to infinity. That derivative is not defined. That's one of the reasons why the step function and the delta function or the impulse function are related like that. This will take care of my discussion for the special functions, and we will see multiple instances in which they're actually useful as we start going through and taking a look at Laplace transforms.